Hey guys, so we've talked about a lot of mathematical tools that we're going to use in this next part here. We've talked about vectors and how to use vectors, how to add vectors. Now what we're going to do is we're going to go on and we're going to talk about projectile motion. Okay, we're going to start off here today. We're going to talk about what projectile motion is, and then we're going to talk about projectiles launched horizontally. And then in the next lesson after that, we're going to go on and we're going to talk about projectiles launched at an angle. And hopefully that will help us be able to solve problems involving projectile motion. Okay, so what is a projectile? A projectile is an object that is, it's like thrown or it's launched into the air, and it is moving under the force of gravity, something like this. Okay, a projectile is going to move in like a parabolic path, right? It's going to go up, it's going to reach its high point, and then it's going to go down. You might see a picture or something like what you see right there. Thing about projectile motion is really tough to analyze by doing just one problem. Usually you need to analyze projectile motion in two problems, and let's talk about what that means. You should see a picture up here. This is a strobe picture of a red ball being dropped straight down and a yellow ball being shot off at an angle. Okay, it's shot off horizontally there. And if you look at them and you kind of analyze them, you can see that as they fall, they are at the same point all the way down. So their vertical motion is identical. So this yellow ball, its horizontal motion is completely independent of its vertical motion. And so when we're looking at a projectile, we can take its vertical motion and its horizontal motion and do two completely different problems with those two dimensions. And we can use that to analyze its motion and make it a little bit easier for us to predict what's going to happen to this object. Okay, just a couple of notes on terminology here. When we're talking about projectile motion, the horizontal motion and the vertical motion are completely independent of each other. So we could be talking about the object's velocity in the horizontal direction or its velocity in the vertical direction. We could be talking about its acceleration in the horizontal direction or its acceleration in the vertical direction. And so generally what we're going to do is a lot of times with the variables, we'll put a little subscript on it to indicate which direction we're talking about. So for example, if I'm talking about an object's velocity in the horizontal dimension, then I might put a little x next to it. So I might say Vx. You would technically say V sub x, some people would say, or just say Vx, some people would say. If we're talking about its velocity in the y direction, in the vertical direction, then we could say V sub y, or Vy, some people would say. We could do the same thing with really any variable. We could use, say, acceleration in the horizontal direction. We could call it A sub x. Or in acceleration in the vertical direction, we could call it A sub y. Usually though with the displacement, remember delta x we learned. If it's in the vertical direction, we'll call it delta y instead of delta x because it's in the vertical direction. Okay, and then as we are talking about projectile motion here, there are some equations here for us to use. So let's talk about them real quick here. These are the same kinematic equations that we learned before. They're just kind of fine-tuned for either things working in the vertical direction or the horizontal direction. So take a look at them here. For objects that are moving in the vertical direction, there's three equations there. You can see it says VYF, so the final velocity in the y direction is equal to AY delta t. So it's equal to the acceleration in the y direction times the time. Let's see, the next equation there, it says VYF squared equals 2AY delta y. So the final velocity in the y direction squared is equal to 2 times the acceleration in the y direction times the displacement in the y direction. And the third equation there, delta y equals 1/2 ay delta t squared. So the displacement in the y direction is 1/2 times the acceleration in the y direction times the time squared. And then you'll see there's one equation there for an object's horizontal motion, because usually with these problems for a projectile, there's no acceleration in the horizontal direction. There's something working in the vertical direction that causes acceleration, and that's gravity pulling things down. But in the horizontal direction, usually there's nothing causing an acceleration there. So this kind of assumes there's no acceleration in the horizontal direction. So there's only one equation there. This is delta x equals vx delta t. So the displacement in the horizontal direction equals the velocity times the time. So those are 4 equations that we're going to use to solve some problems there. So let's take a look at some examples. Okay, here's some examples. Let's take a look at it here. This first example, it says the Royal Gorge Bridge in Colorado rises 321 meters above the Arkansas River. Suppose you kick a rock horizontally off the bridge. The magnitude of the rock's horizontal displacement is 45.0 meters. Find the speed at which the rock was kicked. Okay. Now, just like most problems, it's often helpful to draw a little picture to help you understand what's going on. So, I can draw a little picture there, and I can understand that my rock, it's a rock, right? He's kicking a rock off of the bridge, is moving down. And how far down is it going to move? It's going to move down 301 meters. And that sets off my brain and says that should be a negative because it's moving downward. And it tells me how far from the bottom of the bridge that this rock lands, right? It's 45.0 meters. So it's going to go this far, 45.0 meters. So I can look at the picture and I can kind of understand some of those things. And that's going to help me pull some numbers out of here that I know. So I'm going to make a list of the things that I know and what they're asking me to find. So the first thing, that jumped out at me that I know is how far down the rock is going to go. And we're going to call that delta y. It's vertical displacement, delta y. And that was, we said negative 321 meters. And we also know its horizontal displacement, which we call delta x, was 45.0 meters. We know another thing that they didn't tell us, but we know. We know the acceleration in the vertical direction, because what's causing the acceleration in the vertical direction is gravity. So ay is g, which is negative 9.81 meters per second squared. And then the question is asked us to find vx. If you think about this rock being kicked off of the bridge, the only velocity it had at the very beginning there was its velocity in the x direction, which remains constant because there's no acceleration in the x direction. So what they're asking us to find there is v sub x. So now, here's the thing. I have an equation that'll help me figure out v sub x, right? I have the equation, let's see, what is it? Delta x equals v sub x delta t. And that'll help me figure out v sub x. But the thing about that is if you look at the things I have listed, I don't know delta t. I don't know delta t. So I can't put those numbers in that equation and solve that and figure that out. I need to find something else first. I need to figure out delta t first. So instead of directly attacking the problem, looking at the things in the horizontal direction, what I'm going to do is I'm going to use the information that they've given me about the motion in the vertical direction and find the time. And then I can go back and use this equation and find what they asked me to find, v sub x. So what I'm going to do is I'm going to look at those other 3 equations, the vertical equations, and I'm going to pick this one, delta y equals 1/2 a sub y delta t squared. And I'm going to use that to find delta t. So I'm going to put in the numbers that I know there. I know delta y is negative 321. I know a sub y is negative 9.81. So I'm going to put those numbers in there. I'm going to kind of simplify it a little bit. A half of negative 9.81 is negative 4.90. I'm going to divide both sides by negative 4.90. And then I'll take the square root. And I know, and so then that tells me that the time is going to come out to 8.09 seconds. Now I need 3 significant figures there because all the numbers I started with had 3 significant figures. And it's a time, so it should be in seconds. All right, now let me go back to my list of things that I know, and now I know what now I know what delta t is. Delta t is 8.09 seconds. So let me add that to my list of things, and I'm looking for v sub x. So now I'm going to choose that equation, delta x equals v sub x delta t, and I'm going to put the numbers in there, and this should be a very simple one to put the numbers in and solve. So delta x was 45.0, v sub x is what we're looking for, and delta t was 8.09. So we put the numbers in there, we'll divide both sides by 8.09, and v sub x comes out to 5.56, to 3 significant figures. And that's a velocity, so it should be in meters per second. So, a lot of these problems are going to go this way, where you're going to try to figure something out about the horizontal direction, but you won't have enough information. But you can take what they give you about the vertical direction and find another piece of information and apply that to figuring out something about the horizontal direction. Okay, real quick, another example here. It says a baseball rolls off a 0.70 meter high desk and strikes the floor 0.25 meters away from the base of the desk. How fast was the ball rolling? Now you could draw a picture for this one as well if you want. It's going to be very similar to the last picture. I'm going to forego drawing the picture for this. It's okay, I can pull the numbers out and understand what they mean. So the first number there is 0.70 meters. That was the height of the desk. So this is how far the ball is going to travel in the vertical direction, the vertical displacement. So this is delta y. Delta y is going to be negative 0.70 meters because it's moving downward. That next number, 0.25 meters, this is the horizontal displacement because it lands this far from the base of the desk. That's the horizontal displacement. So delta x, 0.25 meters. And then I also know the acceleration in the vertical direction. That's, g, negative 9.81 meters per second squared. And the question is asking me to find v sub x. So how fast was the ball rolling to begin with? That was its, velocity in the x direction. So I'm going to, first thing, I'm going to use the same equation, I'm going to use the same strategy that I used in the last problem. So the first thing I'm going to do is I'm going to go about finding the time. How much time did this motion take? And I'm going to use the vertical direction to do that. So I'm going to choose the equation delta y equals 1/2 a delta t squared. I'm going to put the numbers I know in there. So negative 0.70 equals 1/2 times negative 9.81 times delta t squared. And then we'll simplify and we'll do a little bit of algebra, and delta t comes out to 0.37 seconds. So I can add that to the list of things that I know. I can add that to the numbers that I know. And I can go ahead and take this other equation for the horizontal direction, delta x equals v sub x delta t, and I can put some numbers in there and solve for v sub x. So delta x was 0.25. V sub x, we don't know, that's what we're looking for, and delta t was 0.37 seconds. We'll divide both sides by 0.37, and v sub x comes out to 0.68 meters per second. Okay, hope we're all having fun. There's some projectile motion problems. We've talked about, vertical and horizontal directions and how we can separate those for the projectile motion problems. Next time, we'll talk about projectiles launched at an angle. So not just things rolling off the desk or kicked off of a bridge, but things actually thrown up into the air at an angle, and how are they going to move and how are we going to solve those problems. So hopefully that gets us a step closer to being able to solve projectile motion problems. So until next time, take it easy.